Thank you. Thanks for the invitation. The topic of my talk doesn't fit the workshop topic, but Eero asked me to talk about it, and of course he's not here. So you can blame him for this. But I'll try to, but it's still fermionic, so at least we have the fermionic stuff, right? So what I'll do, I'll introduce a little bit more motivation for what we're doing, because the main part of the talk will be about something that we haven't seen, I think, during this semester. So I will try to hide lots of background there, but I will give you some idea of what we've done. So this is joint work with 3 people listed here, and it's related to something that 3 of them did in different combinations, also with Sergio and Vecchi, so I'll mention it a little bit later. So the whole idea of this project was to continue with Euclidean QFT for fermions. And for this, we just want to remind ourselves what was done before, mostly for bosonic case, because in that case you see more of the stochastic analysis, but you want to see why we're trying to build something parallel to that, but very, very much different. So of course it goes back to Ed Nelson, and who had a series of papers in '73 about this, and more or less, I will not even list all these axioms of Osterwalder and Schrader, but more or less that gave you a way to go from Euclidean QFT to what they wanted to construct when that was the first huge attempt to do constructive QFT, and we just assumed that we kind of have a way to go between these theories. And what he observed there also was that for the bosonic case, you really get to this Markovian quantum QFT and things like that, and therefore this is where probability comes in, and this is what we want to have a parallel picture of for fermions. So I'm just mentioning these basic references in this case, just so that we... yes, this is a quote from Ed Nelson, which is probably relevant to this trimester, where he says that, yeah, people reacted in horror to attempt, to use probability. So since then, I think people get used to the idea of using probability. What we'll do, we'll actually do non-commutative probability here. So, so this is what they tried to do. This is the idea was to construct for the bosons to construct this measure. So there is no pointers, and I'm very short. So I will try to point to this measure new here. So things in red are the ones that we don't usually have very good mathematical description of, right? And the main thing was to have something for without interaction, and then that corresponds to something that we as probabilists know, which is something like Gaussian measure, even though on a space, a more complicated space, and then add in interaction and hope that we can build something from that. So that was the idea. As you can see, this goes back to more or less my initial background in constructing something on infinite dimensional spaces. Okay, and this is not what we can do for fermions, and I'll explain this later. So the one other point of view, which is stochastic quantization, came from connecting this measure that we want to construct as the stationary solution to this SPD. So this is where the SPD picture comes in, and again, we'll have that maybe at the end if we get there. So these are two things that we want to keep in mind. So we want to have something like this for fermions, where we would have some probability-like measure, SPDEs maybe, and we'll have the SPDEs and then an invariant measure or stationary measure for this, if it's a measure, will be our replacement of these objects for fermions. So this is the idea. So what are the problems in doing so? Well, instead of symmetric tensors of one particle state, you of course have anti-symmetric things. And it seems that at first everything is kind of okay. You take this Bayesian integral, you construct something, again, it consists of, so G here is the covariance of your Gaussian piece for fermions. You have a potential V, and you want to construct both pieces here, right? So the same thing. So I will not talk much about what kind of potential you can take. We have some concrete examples. The goal was actually to construct at least some examples where you can do this. So this is all very classical, nothing new here. So what do we mean by having a Gaussian? It's this first displayed equation there, right? So the covariance is an operator, and you have this rule that it satisfies for any vectors that you fit in. So as I said, Sergio Ribeiro with another former student of his, Francesco and Max, and then there was another paper where they did the stochastic quantization piece for Grassmannian measures, and this is where they tried to build singular SPDs and forward-backwards SDs in this context. So what didn't work there was that to get to the models they had in mind, they actually needed multiplicative noise, and this really, that was only for additive noise, as we'll see later. So when I joined the project, what we wanted to do was actually to build a Grassmann stochastic analysis, which is what we did. And this just appeared, the result of this. And actually, if we get to this example later, I'll mention concrete examples where we managed to build, for example, this fermionic measure on torus as a fermionic counterpart to what Nelson did for bosons. And we had several examples, very concrete, but what I will try to convince you in that we had several approaches to this, and I will explain why they don't work, not technically, but fundamentally, and why the construction ended up to be so complicated. Okay, so I'm just trying to hide the complicated part to later, so that not to be as scary, I guess. So what do we want to do? We want to, since we have this non-commuting, potentially non-commuting random variables, the typical approach to this is to take values in C-star algebra or phenomenon algebra. Okay, so what is it? These are bounded operators that have all these properties. Fourth line there. And quite often you can think of this as just bounded operators on a Hilbert space, sometimes finite dimensional, and I'll give you an example of Clifford algebra later, which is relevant to what we are discussing. So we also want to measure things there, so instead of having measure integral, so I don't think about the measure as measure, right, on something, but rather of integrals corresponding to the measure. So instead of that, we have what is called state, so positive state, so that we can find the expectations of our random variables. Okay, so these are the objects we need. So eventually, our goal will be to find an appropriate C-star algebra, von Neumann algebra, and maybe trace or state there. So I did say trace, right? But actually, we'll see that it's not good enough for us. Okay, and this pair is what we call a non-commutative probability space. Actually, this includes the usual commutative probability space, where we think of this as L infinity, so multiplication operators by L infinity functions is your commutative analog of this. Okay? Still okay? So instead of measure, we want actually to find this trace or state on C. Okay, so what they did, they looked at this on particular Grassmann. So this what they did for Grassmann random variables, and what they managed to do was to construct a homomorphism of this Grassmann algebra into C-star algebra C. So the C-star algebra C should come from model that you're looking at. So right now it's very abstract, but when you have a particular question, you actually want to find a very concrete description of this C-star algebra. So what do we have? We start with a vector space V. We have skew symmetric tensors because we have fermions. So the scale is the first zero level. We assume that there is a vacuum vector, which sometimes is denoted by omega, sometimes by 1. And then we build the Grassmann algebra over this vector space. So the vector space can be finite dimensional, can be Hilbert space, depends on what you want to do. So, and then we treat a Grassmann random field as map from this vector, from the vector space V to your C-star algebra. So why I put it in red? Because I want to remind ourselves every time that we have to find it. We have to construct it from whatever we have in mind. And since we have this non-commutative skew-symmetric tensors, you have this simple rule here that every time you change the order, you get a minus. We still okay with this? Okay. So then, again, that's what they did. They extended it to the whole Grassmann algebra here. I'm still trying to use the pointer Grassmann algebra here. And they said that it's possible to do. And actually, you do it explicitly. You check that everything works okay. And actually, the initial inner product on the underlying vector space V induces an inner product on your Grassmann algebra. So this is very kind of standard stuff, but still it's useful when you apply it for these random variables. So as I said, we want to find this appropriate C-star algebra and state trace there. So of course, if you're dealing with fermions, the first thing that comes to mind is to use a Clifford algebra. And it's been studied. So I'll tell you why. There are more than one reason why we wanted to do this. One is because, yes, that's your fermions are here. So what is it? So it's a C-star algebra. Actually, it's a hyperfinite one factor, which we'll come back to later, which is generated by creation and annihilation operators, which are labeled by points in your underlying space. So usually it's this V is a Hilbert space, and actually you can take approximations to this whole construction by approximating your Hilbert space by finite dimensional spaces, so you get finite dimensional C-star algebras generated by creation and annihilation operators, and they satisfy this canonical anti-commutation relations, which is written right there. Okay, so it comes equipped with the conjugation, which comes from, so you induce this action here on annihilation operator. So this is all well known. And the good thing that it comes with, which is something that my father taught me many years ago, is that it comes with a trace. And so in this case, you have a very natural setting for for the fermions, right? This is why they were interested in this. So you have your vacuum, you have all the structure, and it's a trace. This is what it says here. So you can switch A and B, and when you evaluate it with respect to tau, you get the same thing. So, as I said, this is an example of a hyperfinite to one factor, which is unique. So if you want to do any computations, you can just take this realization and deal with this. It's very concrete. It seems very abstract, but actually lots of things reduce to dealing with your underlying vector space or Hilbert space. Because at the end, you can reduce things to how it behaves on that space. So it's a very, very good example where you can do lots of things. Hyperfinite means that you can kind of approximate it the way I described before, by approximating the underlying vector space or Hilbert space. So we started with that, and we thought, okay, why not do that? And you run into problems almost immediately. So the one thing that you observe is that if you try to, so what you want to do is you want to construct a Brownian motion first, and that means Gaussian Grassmann variables come in, so we've seen it before. And what you need to do is you want to have this covariance operator, and from all this machinery that I described before, we got to the Clifford algebra. You can see that it's a bounded operator on your underlying vector space, and it is anti-symmetric. Okay, so when you, so then you build your, so this is what they did previously. I'm listing it here because, again, this is what we tried to use in the beginning with a particular choice of sister algebra, which is the Clifford algebra. So then, what is Grassmann stochastic process? It's like the same thing that you do in the usual spaces where you can construct the stochastic processes. So it's indexed by positive numbers, right? You have this Hilbert space there. The Gaussian Grassmannian noise is defined by the covariance you have. So the C should be G, of course, from the previous slide. I thought I changed all of them, but no. So this is this covariance I had. So I changed it to G because C is used for the sister algebra. I didn't want the notation to clash. Okay, and then you would try to build a Brownian motion from this by kind of defining it as the integral of this noise. Okay, with some properties. Okay, so that was actually done by them, and they looked at non-singular SZ. So this is the first paper where Sergio was involved. So they proved existence and uniqueness, and the point is it's with additive noise, and they actually proved that there is an invariant measure, which you remember is our goal, right? Because this invariant measure might be the object we want to have to go back to the stochastic quantization for Fermionics. So there was another approach here, so I will not talk about this, but it deals with different, so this is for singular case, and again, we're not using this directly. What we did use was the approach to how you build stochastic processes. Okay?
Masha.
Yeah.
Sorry, not to take too much of your time, but are those equations at the level 1 after you take the expectations, or
No, they're actually parallel. Okay. But we'll see them.
Okay.
We'll see some of them. I also want to mention that, as it happens, it seems, there was another group of mathematicians working on similar questions, and we finished this project approximately the same time, and it turned out that we used different tools or different approaches, so I'm just mentioning here Chandra, Hare, and Pev. And they used what's called local C-star algebras. I will not explain what it is, but their goal was to solve some singular SPDs. Okay. So what are the problems with this setting? So one of them was that we usually want to multiply things in these algebras. So if you have, remember, this is how you create your functions, right? And in the simplest example we wanted to deal with, actually, if you take a product of two of these functions, they are not in the C-star algebra you started with, which is kind of natural. So this was an indication that we needed something larger than your C-star algebra. So what is phonemic algebra, C-star algebra, in what we'll see right after this? Usually these are your L infinity, right? So if you multiply things, you might get out of L infinity, which usually means that you should have LP-like spaces, okay? Actually, if you want to do any reasonable stochastic analysis, you also probably should have some kind of LP spaces to solve your SDs or SPDs, whatever you want to do. And of course, you see the same, and I think that answers your question here. So if you want to, like, how do you build your stochastic integrals? You usually take your Brownian motion multiplied by the integrand, whatever approximation you're using. But the main thing is that you want this to converge at least sometimes. And you can see very easily that it's not going to converge in the phonemic algebra. So you need to have a larger space of objects to do this. So, yeah, no problem. We can do this, right? Actually, it was done first by Erwin Siegel, who said that if you have phonemic algebra, C-star algebra, phonemic algebra is what we actually need here, and if you have a trace, exactly like what we have for the Clifford algebra, that's your prime example of that, then you can take LP with respect to this trace, so which is defined here. Okay. So what are these objects? Okay, you can. There are different things that you. So one of the, and I didn't put this example here, but if you take, say, phonemic algebra to be all bounded operators on a Hilbert space, you take the usual trace. So what you get as your LP is what we call Sutton classes. So L2 are Hilbert-Schmidt operators, L1 are trace class operators. So we know something about this, right? And quite often you can actually describe them in this setting. Some operators are not bounded anymore. That's fine. So they still are operators on your initial Hilbert space. So there are lots of people who are studying this kind of thing, so I'll mention some of them. And essentially we went through lots of these constructions and none of them worked, and I'll explain why. Okay? So the main thing to remember here is that we still need this trace to make sense of this construction, and of course Siegel was one of the first people who did this, and then there was this whole industry of people doing it in other math fields. And more or less, one of my tasks was to tell my co-authors that there is this construction, and then they would come back to me and tell me, oh no, it doesn't work. Okay, so in this case, you actually have Hilbert's inequality, which was one of the things that we wanted. And if you want to construct some analog of your commutative probability spaces, what you have is you need to have a filtration. So in this case, the filtration is filtration of phonemic subalgebras of your phonemic algebra C, and then you can define conditional expectation because, you know, at the end we wanted to do martingales and things like that. So we really wanted to have, yes?
In the formula for the conditional expectation, did you have C sub t as opposed to C on both sides? I'm a bit confused by like tau t appears on both. Both the map is called tau t and the trace on the second.
Yeah, I think, oh, yeah, that's.
Is that a typo or?
Actually, no, because this is a trace from T, right?
So you have multiple traces on the same algebra.
On the subalgebra. I think I have T missing here.
Oh.
Yeah. Thanks. Is it okay?
Yeah. So what is that increasing filtration of algebras? Can you say? C sub t is what?
Is a sequence of subalgebras of your large fundamental algebra C.
I see. We don't know yet what it is. Okay.
We are not dealing with any examples either, right? So you just fix this filtration and then you construct your stochastic process with respect to that. Depending on this choice, you get different properties, right? So this is again a large field that I will not really discuss here, but several major earlier results probably we should mention, and in particular what Karen and Lee did, and they did prove hypercontractivity, so that really goes back to this motivation of what Ed Nelson wanted to do, right, but for Fermi fields. And also there were attempts to construct stochastic calculus for this Grassmann and Fermionic processes before. So, and I think the main work was done by Bernard Streeter and Wild, I think. I'm still not sure how to pronounce his last name. And so what they call the Eta-Clifford integral, so they actually had a couple of different papers. Also, there is a discussion by Streeter on why reflection positivity is so important and things like that. So they were really doing all this in this direction, then it stopped. For different reasons. One of the things that you see here is that, yes, they built it, but actually they could only do L2 theory. And if you want to solve anything reasonable, right, you should really go beyond L2 theory. And so either calculus is there, but anything else is not. Okay, so what we discovered at this point, and this is what this red bullet point there says, that I did mention before that this covariance for the driving noise would be anti-symmetric, and actually when you put it in trace, remember it commutes, it doesn't see the order in some sense, you can see that it forces the covariance to be zero. I will not explain it here, but you can see. And therefore, it means that if you have your model built on a sister algebra with a trace, you will not be able to build any reasonable theory of stochastic, Grassmann stochastic analysis here. And this means that you have to go beyond that. Okay, so I'm also mentioning this paper by Van Gross where he actually did this LP theory for Clifford algebra. It's more readable than Siegel, I think, even though I like Siegel's writing. But many people find it very difficult. Okay, so the next candidate was, of course, so instead of, for those of us who like phenomenal algebras, to go beyond 2-1 factors and go to the world of what these people did. So it comes with name of two Japanese mathematicians, Tomita Takesaki theory, and so what they noticed was that if you So the main thing here is that you see that omega now, and I will not give you definitions, I can give you them later after the talk, not right now, that instead of a trace, we now only have states. So this omega of AB being equal to omega of BA is gone, okay? So we don't have that. So this is our hope for having a nice Brownian motion so that the covariance is not zero, okay? That was the choice. And then it was also clear that you really have to go beyond this hyperfinite P1 factor and to go into the world where this picture is non-trivial. So, so if you see, so the sigma t and this delta, these are modular operators or modular operations that are connected to phenomenon algebra, and of course this M should be C, sorry. What we want to do, we want to really stay away from omega being a trace. And so to do this, you actually have to have this non-trivial modular operator, and because it measures how far you are from being threshold. Okay? So this is a very well-studied setting. It's very complicated because the models for this kind of phenomenon algebras for which this is non-trivial are complicated, but we looked at a very simple example of that compared to other examples. And this is what we used for our several models that we built at the end. Okay, so as you can see here, let's keep what analytic elements mean in this case. So you see that if I want to measure how omega on AB is different from omega on BA, it's given exactly by the Tomato-Takasaki modular automorphism here. And if it's not trivial, then you have that it's not racial. Okay. Okay, we're okay with this? So essentially, what I'm trying to say is that our attempt to construct the stochastic analysis, Grassmann stochastic analysis, forced us to go beyond something like Clifford algebra as our object that we want to have around, because we wanted to have a non-trivial theory. Still okay? Kind of. Okay, so the next thing is, do we have LP spaces? So you hope that we're close to the resolution. Unfortunately, no. So yes, there are this famous Hager LP spaces. Lots of people I know who are studying them, and that was our hope. And of course, at the end, what you see here is, yes, LP, LQ, actually it's trivial, I forgot to write that. So essentially, you cannot build any kind of stochastic analysis because you want to multiply integrand with an increment from your Brownian motion and to have something in LP space or LQ space, and you cannot do this here. So more or less here the problem is, how do you treat products of elements? Because you want to be able to say that if I have two elements from LP, for example, I multiply them, I get an element for another LQ, right? And you cannot do it here, because you will always get out of this.
Sorry, I thought that Hager's LP spaces do form an algebra in the sense that LP times LQ lands in L1/Q.
Not as far as, but we can maybe talk about it later. One of the attractions of this setting was also that people like Pizier and Marius Junger and other people studied Burkholder type inequalities there, which are also needed to construct stochastic integrals, but at the end we realized that we couldn't deal with multiplicative noise, and so we abandoned this this approach. So what we did, we introduced what we call twisted LP spaces, and what they actually did, they used this modular Tomita-Takisaki. So let me just quickly remind you. So this sigma t is this Tomita-Takisaki modular automorphism, and this is what we use to kind of change the state that we used and introduce LP spaces with respect to that. And so then what you have is that LP is, so you have an increasing, you have this relation between LP and LQ. You also have that analytic elements C sub A are in all LPs, and you do have Hilbert's inequality. So the first version of this was in this paper of Majewski and Zagravinsky for a particular tau that we have there. And so we just extended that and tried to build our stochastic analysis with respect to this construction. We okay with this?
Tau is that a number, right?
Yes, it's the, it's not the tau we had in the beginning. I think I'm running out of flags, yeah. But I think that's what we used in the paper, that's why I used it. Okay, so it's just a number. And it can be 0, and then you get back to this paper by Majewski and Zagravinsky. Okay? And so then what we did, we actually used this construction for at least one example of such sister phenomenon algebra, which is the Arakeles representation. And I realized that there are lots of little symbols here, so we'll just only say here is that, so we take a Kerr algebra on 2 copies of your underlying Hilbert space, for example. You have a non-tracial state with our means quasi-free. We'll not talk about that for sure. And then you create this annihilation and creation like operators A and C, and then you take a phenomenon algebra which is generated by them. So what this 2 prime here says is that you take second commutant to get your phenomenon algebra. So you take this generating set and then you get the phenomenon algebra. So it inherits the this anti-commutation relation that we had. And actually, in this case, so there are very few cases where you can actually compute this modular operator and modular automorphism directly. And here you can do this. Again, I'm not even explaining what these objects are, but this was done long before we did this. We just used this construction to test our approach on. Okay. So then the first thing you do is you construct Gaussian. So this is what we did here. And in constructing this, we actually use heavily that the modular operator is not the identity operator. And this exactly where we need also that it's not a trace. We are in non-tracial case. So then what you do first, you look at how this Gaussian random fields behave in our new LP spaces, and we proved hypercontractivity. We also defined Brownian motion, similarly to how they did previously, but for this non-tracial case. So again, this T is G here. Of course, oh no, it's actually C because it comes from, yeah. So you have a covariance operator, and because of this twist now, we don't have to have it 0, okay? you have this conditional expectation introduced as before, and we do take a filtration which is generated by the Brownian motion that you constructed before. And so finally, one of the things we were able to do was that now that we could multiply things, we can actually define either integral in this case. And then get all the things that you expect from stochastic analysis, which is eta isometry. And again, I'm mentioning that eta isometry, I think, was done by that paper many years ago, different construction, but still. And also you have Burkholder-Davis-Gandhi inequality, which is needed, again, to do stochastic analysis, to define stochastic differential equations. Also, you can, so we use Grassmann theorem, that is, we proved Grassmann theorem that we used to deal with solutions to this SDEs. And in some sense, you can say that it really is classical, but in this very non-commutative setting. Okay, so we try to come up with ideas that, or methods that were similar to what you see in the commutative world, but for this non-commutative LP spaces, which are fit for whatever models we have in mind. Okay, so I'll finish with mentioning several examples, and maybe theorem later if we get there. So what we did, we were able to construct this Fermionic measure on the torus, as I mentioned before. So that comes from solving this as SDEs. We actually also, that comes for almost for free once you have this, the existence. So we have an analog of stochastic quantization again in this particular case, which is an analog of the bosonic results of. And yes, you have interaction which probably can be adjusted to polynomial, which interaction which I will not talk about. But at the end, I find the construction to be a little bit too, how to say it, mildly complicated, right? Which usually means that you're missing something, but okay, I'm missing something, not you. Okay, so what was the construction for the torus? You start with the usual space, underlying space. So you have these fields. So here's your covariance that you use. And you can actually see that these are not functions like in the symmetric case. And so what you actually have is this distributions here on the best of space with values in analytic elements of your footprint, the phenomenon algebra. Okay? So you take the potential as I mentioned before, and what you prove is that that you can actually make sense of this quantity, and it's in all LPs, and you can actually prove that there is expectation that you need, right, to construct solutions, which is the last theorem here. So this, it looks kind of easy, right, once you construct all of this, but I just tried to explain why we went through trouble of, so I didn't want to give you this twisted LP spaces in the beginning because I wanted us to walk through all other attempts which seemed very natural, but they didn't work for fundamental reasons, not because we just couldn't prove something. They just don't work for this setting. And I think that's it. I hope. Let's recap that we don't need, right? Okay. I'm just looking at you and yeah, like, why would we do this? Okay, so Brownian motion here is given. So you see, like it looks very much like what you expect, right? So except that you have all this complicated, it takes values in complicated spaces. But the idea was really to construct something that looks very much like what you expect from the commutative case, and in analog with the bosonic case, right? Also, but and we even have Ita's formula, and there are lots of questions that one might ask about how this generator behaves, right? So there are some mathematical questions that might come from this. Whether it's a useful thing to build more models, I don't know, but that's what we did. Thank you.